Okay, let's start. So last time we considered this Weierstrass P function. So we have already proven that a holomorphic elliptic function should be a constant, and there is no elliptic function with only one simple pole in a parallelogram. So the simplest non-trivial elliptic function should have one double pole or two simple poles. And we constructed a function, elliptic function with one double pole in a period parallelogram. So the idea, naive idea was that, since we have such a principal part at any lattice points, so we are constructing an elliptic function with poles at lattice points. So just summing up such terms could be an elliptic function. And this is true for third or more order elliptic functions. Namely, if this exponent, so order of the pole or order of the elliptic function, is larger than 2, not equal, then such series, double series, converges absolutely and uniformly on any compact set. So it gives a meromorphic function by Weierstrass theorem. And by construction, it is obvious that it has an order n. And so it seems to work, but for n is equal to 2, such construction does not work because this series does not converge. If this is 2, then so we have to correct each terms. Okay, with that, this term, it was the series which we used to construct elliptic functions of order 3 or more. But to get an elliptic function of order 2, we have to subtract something from each term to get a convergent series. And well, it works, and we get such a elliptic function of order 2, which is even. And yeah, the Laurent expansion to 0 has such a form. Actually, this constant term is 0. And using this expansion, we can show that P satisfies this differential equations. So first order. And well, by solving this, we can say that P gives the inverse map, inverse function of this elliptic integral. And actually, this coincides with the construction of P function as the inverse map of the Abel-Jacobi function, Abel-Jacobi map. And well, actually, the Riemann surface or elliptic curve is constructed as a set of ZW which satisfies such equation, or we can give a map from this torus C over lattice to the elliptic curve. And actually this is the inverse map of Abel-Jacobi map. And to show that this is bijective is one of our homework program here. So this part is the program. Please show the bijectivity. And it gives an isomorphism, namely it is holomorphic as a map between W and R bar elliptic curve. And well, yeah, where was it? And well, yeah, P function is such a fundamental elliptic function in this sense that any elliptic curve is a rational function of P function in this form, and which can be shown elementary by using complex analysis and some arguments using the theorem on elliptic functions. But well, you see, this is the proof, but it's a bit messy. So please try yourself. It's rather elementary, but still, yeah. If of course I can tell you details, but it is rather tiresome, and probably you do not want. So now let's move to the other fundamental property of the P function, the addition formula. For example, as you know, sine has such an addition formula, or as we saw, well, it was a long time ago, but I think it was February that we showed such an addition formula for Jacobi's Sn function. Actually, such a addition theorem can be understood as a consequence of the structure of the elliptic curve elliptic curve has a structure of additive group like this, and it is reflected to this theorem. And well, we can show that any elliptic function has an addition formula, but the fundamental one is the addition formula of P function, which is stated like this. Well, if 3 points U1, U2, U3 are summed up to 0 or modulo the periodic lattice, then such a determinant is equal to 0, which is of course a polynomial expression of P and P prime. And as you know, P prime is not function, so it is, we can replace P prime U3 by this, and since P is an even function, we can replace P U3 by this. So this has this states some relation between values at U1, U2, and at U3, U1 plus U2. Okay, the proof is elementary. Probably Natalia has encountered this proof in their seminar of complex analysis. But let me repeat. Okay, we can let's assume that the values of U1 and U2 are different. Well, when they coincide, we can afterwards analytically continue this relation to such values. So there is no problem. Such set of U1 and U2 is dense open set in our C2. So we can, if some equation holds on this set, it automatically holds on all points in C2. So, well, under this assumption, we can solve such a linear equation for A and B. Well, the exact explicit formula for solutions A and B are not required further, but well, in some exercise you should use this. So let me write it down here. Anyway, here we use this assumption. So the denominator does not vanish. Well, actually, in order for this equation to be non-degenerate, these coefficients should not coincide. Okay. Now, well, let's consider such an expression, which is obtained from this equation by subtracting left side from right side. Of course, well, as a function, this is an elliptic function because this is elliptic, this is elliptic, and of course constant is an elliptic function, so this is an elliptic function, and it is of the third order, namely it has a third order pole at lattice points. So in a single period parallelogram, there is only one third order pole. So it is our elliptic function of third order. Well, yeah, P prime has a third order pole here. P is second order pole here. So third order pole is stronger than second order pole. So pole of this P prime covers the second order pole of P. So what can we say about third order elliptic function? Well, by one of the theorems which we proved 2 weeks ago for general elliptic functions, there are 3 points where f vanishes. Actually, we know 2 of them because, yeah, U1 and U2 satisfies these equations. So, well, but there are 3. So let's call it U0. Then what can we say about this U0? There was another theorem on elliptic functions. So sum of zeros is equal to sum of poles. We proved this 2 weeks ago. And pole of f is at, sitting at 0. So this is 0. So sum is, of course, 0. And 0 is U1, U2, and U0. So sum of them is equal to 0. Which means that, well, up to period lattice. So U0 and U3 are congruent modulo gamma, which means the values of an elliptic function does not change by shifting by gamma. So f at U3 is equal to f at U0, which is 0. Okay, what does this mean? This means that, well, yeah, of course, this. And since f is equal to P prime U minus A P U minus P, we have such a matrix equation. I just rewrite this in a very, well, elegant or good-looking manner. P prime U1 minus A P U1 minus B is equal to 0, for example. What does this mean? Well, here is a non-zero vector. Non-zero because here is 1. So if non-zero vector satisfies such an equation, then by linear algebra, A should be degenerate. Namely, determinant of A is equal to 0. probably everybody here knows well. So this determinant is 0. Which is this one. Okay? So we have proved that P function satisfies this addition formula. Well, although we call this addition formula, but it includes not only P of U1 plus U2, but P prime of U1 plus U2. So it is not of this form. For example, sine of U plus V is sine U cosine V plus cosine U sine U, or well, Sn U plus V satisfies this, which means that Sn of U plus V is expressed in terms of values at U and V. Here we do not have such a formula, but well, fortunately, we can write this in this way. Well, this is one of, again, homework problem, because this is not very complicated. This well, there are so many homework exercises because we do not have much time left. Okay, P, the value of P at U plus U2, U1 plus U2 can be expressed in terms of P of U1 and P of U2, as well as P prime of U1 and P prime of U2. This is not a big deal. Well, yeah. Or you can prove such an equation. Of course, they are equivalent. And well, it is rather easy because, well, yeah, so this is equal to P of U3 and, well, how can we find such sum of PU1, PU2, PU3? Well, actually, these values satisfy a cubic equation, which can be obtained from this differential equation and this linear equation, which we used in the proof of the addition formula. And so, well, yeah. So the yeah, the rest is your problem. I do not explain more detail. Okay. Anyway, we can express P of U1 plus U2 in this way, which is well formulated additional formula like this. And well, actually, we can interpret this addition formula geometrically, but well, yeah, I explained it in this last homework program in detail. So, well, yeah, here is a misprint addition formula. So, please consider yourself. Any questions up to now on P function? I mean. Okay. Now let's move to the next topic, theta functions. Well, as repeatedly emphasized, everywhere homomorphic elliptic function, namely elliptic function without any pole, is a constant, namely trivial, not interesting. Which means that doubly periodic homomorphic homomorphicity, well, two conditions are quite strong and confine the solution to constant. So we weakened this condition to meromorphic function, and there are many non-trivial elliptic functions. Now we require homomorphicity, but let's weaken this double periodicity in a good way, so-called K-psi quasi-periodicity. Well, to do that, let's use some simplified notations. Well, we have used two complex numbers, omega 1 and omega 2, as pairs, fundamental pairs. But when we renormalize the variable u, well, dividing, or, well, yeah, if we define such a function, then of course this is an elliptic function, meromorphic function, a doubly periodic function, but with periods 1 and such ratio, of course, because of this periodicity of A. So we can normalize one of the periods to 1. Moreover, well, so there are two periods, 1 and since they're linearly independent over R, at least imaginary part is not 0. But well, maybe omega 2 over omega 1 is in the lower half plane. Of course, it is possible. But in that case, we can take minus of omega 2 over omega 1 so that this period has positive imaginary part. So, what I want to normalize this periods, a pair of linearly independent complex numbers to this form with tau in the upper half plane. So we call this tau. And then the period lattice has this form. So yeah, we use this notation here when discussing data functions, which I shall define soon. So if f is an elliptic function with this period, fu plus 1 is fu, and fu plus tau is equal to fu. But we know that this is too strong to have a holomorphic solution. So let's allow some discrepancy, allow some factor here. Why are we choosing such a factor? Well, because we would have good functions. As we will see later. So yeah, just believe me. But here, these parameters A and B cannot be arbitrary. For example, let's consider such shift of the variable u plus 1 plus tau. Then, of course, it is f u plus tau plus 1. So because of the periodicity, this is fu plus tau. And this is sorry. But on the other hand, this is fu plus 1 plus tau. Which is equal to this. Instead of u, we have u plus 1 here. And f of u plus 1 is equal to fu. So these two expressions should be equal. And of course, if f is equal to 0, then it is not interesting. So let's assume that f is not 0. Then these factors should coincide, which means that, well, the difference is here. So E of u, A is equal to 1, which means that A should be a multiple of 2 pi r. So we consider such conditions for this entire function. Well, probably you know, but let me repeat. entire function is a holomorphic functions over all the plane. So now, yeah, we have such conditions. But here we have a periodicity. What should we do with periodic functions? Well, yeah, we should expand in Fourier series. General theory of Fourier expansion is quite a long discussion about convergence or some conditions of Dini or something like that. But here we are considering holomorphic function. So in this case, we can prove such expansion very simply because we know complex analysis. Complex analysis is very strong, powerful. Just consider such a function, which is constructed from F like this. What is good for this substitution? Well, if as you know, log of V is multi-valued. So this cannot be uniquely defined. So how can it be defined uniquely? Well, we know that log V is equal to, real part is determined uniquely, and the problem comes from this imaginary part. Imaginary part is determined only up to multiple of 2 pi. So there are always ambiguity of such term. But this log V of 2 over 2 pi has ambiguity in Z integer. And F does not feel this difference because it is periodic. So G of U is well defined on, of course, C minus 0, except at 0 because at 0 log cannot be defined. Therefore, it has a single singularity here at 0, isolated singularity. So we have a Laurent expansion around 0. Then in terms of F, so let's put here exponential of 2 pi u, or now this is equivalent to this substitution. Then this is just f of u, and the right hand side is such series, which means that we have a Fourier expansion. So in complex analysis, Fourier expansion is very easy. in a sense, it is equivalent to Laurent expansion. Now, well, so we used this periodicity with respect to 1. So now at the turn of this case periodicity with respect to the shift by tau. So we express the coefficient A like this. So this is the case periodicity, which means that well, on this side we just put u plus tau in this expansion. On the other hand, we have such an expression, which means this. So by comparing the coefficients, it's equal to E of minus K, E of 2 pi I n. So by just shifting this. So this should be equal to this, which means that we have an recurrent relation for an. That's fine. So we can determine an from, for example, A0 to, if we have n such values, then we can determine all an by this condition. Well, does this really work? For example, if k is 0, it's okay. We can show that only one term remains here. So it is essentially exponential function. Well, it's not easy. It's not difficult. And consider the case when k is strictly positive. Sorry, not this. K myself. So if, I mean, we should put this here. Well, the problem is again the convergence. Formally, we have already solved this equation, but we want a meromorphic function. So this series should be convergent. For example, let's consider such number. So we can shift this interval by k, and here we have such a number. Then, well, when this is the recurrent relation, and well, let's apply this again here, and we have, sorry, here I have a misprint like this, and well, we can continue k times like this. And then, so we just subtract k m times, and let's get, so the rest is m0. And well, then the result is like this. MB is here, and sum of these them is equal to this. Well, or for example, n is equal to km plus n0. This is equal to km minus 1 plus n0, etc. So this is just for arithmetic progression. So we explicitly solved there are this recurrent relation in this form. Okay, the program begins here. So we used such function to show the Fourier expansion, and the point is that it is a holomorphic function except at 0. So by Cauchy's formula, coefficients of the Laurent expansion can be expressed in this form. And well, yeah, this estimate is quite well known in complex analysis. Just M is some now bound on this circle. So since the length of the circle is 2 pi, this this n plus 1 is becomes n. Anyway, when n gets bigger, this goes to 0. Of course, we assume that R is will be larger than 1. Well, this is just a complex analysis, well, general property of such a function. On the other hand, we know that an is expressed in terms of am0 like this. Let's estimate the absolute value. Well, and this is elementary, and yeah, the rest is that the program is that here we have m squared plus, of course, m, but this is a function of m which grows faster than m. Here there is an expression of m which is linear. So this quantity grows like this when m is large. here Q is E of pi times K times imaginary of tau. And we know that this is positive, pi is positive, of course, K is positive, and the imaginary tau is positive. So this is greater than 0. So Q is bigger than 1. And this diverges to pass infinity, which contradicts with this convergence, which means that there is no such function, alas. But this non-existence is a consequence of this assumption. So let's consider negative K, for example, -1. In this case, yeah, everything is the same as before, and we do not have such a contradiction because here now we have minus. So this is such term vanishes. So there is no contradiction, and we have such an expression for f which satisfies these two equations. And well, so this is a little bit messy, non-essential part. So we simplify this to U, and we call such a series a theta function. Namely, this f is expressed like this in terms of theta. Well, that sounds good, but is this really existing function? I mean, there is no contradiction of this type, but we have not yet shown that this really converges. So sufficient condition and necessary condition are different. So let's prove the convergence of this series separately. Actually, it converges in very good manner. If our imaginary part is bounded, imaginary part of this U is bounded, and the imaginary part of tau is strictly larger than 0. I mean, bounded by some positive number. Then this series converges absolutely and uniformly. And by Wester's theorem, it is homomorphic in U and in tau. Well, the proof is simple. Just estimate each term. The absolute value comes from the real part of this exponent, which is equal to this. And well, we are assuming that this is greater than epsilon, and this is bounded by C. So we have such an estimate for this absolute value. And well, since C is positive, this diverges, but Fortunately, here is square of n, which grows faster than this n. So this series converges. If you want, you can apply some criteria for absolute convergence, like D'Alembert check or something like that. It's not a big deal. So this series is a measurement of this series. So by stress M test, this series converges absolutely and uniformly on this set. And we can take arbitrary C and arbitrary epsilon. So we can show that this converges on any compact set. Any compact set in C times H. H is the upper half plane. And if such condition is satisfied, then we can apply Weierstrass theorem, which states that such a series defines a homomorphic function on this space. Namely, this function, theta function, is entire in U, first variable. And this is homomorphic on this upper half plane in tau. And as we have assumed, we assumed theta function satisfied this periodicity and this case periodicity with such factor. Or yeah, if we shift the variable by any element of this period lattice, we have such an expression. So this was the case for K, which is equal to -1. Actually, for arbitrary case, such f can be expressed in terms of theta function. So, yeah, just try. The point is that we have this recurrence relation. This holds even when k is negative. And so we can express any coefficient from the coefficients in this interval. Or when k is negative, we put something like this. And we can show we obtain a series, something like this, with which is a linear combination of theta functions. So essentially, such a function space is spanned by theta functions. Okay. So we have defined case doubly, not periodic, but case periodic functions, which is holomorphic everywhere. Actually, we need some variants of this simple series. This is it. So we call that theta butal is equal to sum of pi I n squared tau plus 2 pi I n u. So just shift n by some number, u by some number, and which is also called theta functions, but with characteristics. Well, a and b, parameters a and b are called characteristics. And well, as you can guess, such function has similar properties as the original theta function. Entire in u, holomorphic in tau on the upper half plane. Of course, these parameters a and b are 0, then we return to the original theta. And well, there are several properties which relates different characteristics. If we shift b by some number, then b appears only here, so we can add b prime to u, and we get this property. If we shift a, the first parameter, and then first characteristic, and then there are some messy factor here, but well, in principle, it is not a big deal. And well, if these shifts are integers, well, it is very simple, because if we shift a by n, then we can just shift all n by p, then we have another expression without this p. And when we shift b by q, we get some factor here which comes from this, but in principle 2 pi I n, for example, and q is equal to 1 if q is an integer, so there is no big difference between these functions. So we can reduce the variation of this A and B, and actually later we need only 4 theta functions with characteristics of 0 and 1/2, like this. So we have such simple notations. For example, theta 1 is equal to theta 1/2, 1/2. So it is rather confusing expression, sorry, but this is a famous notation by Mumford. Actually, much more used notation is this theta 1, theta 2, theta 3, theta 4, which corresponds to such thetas in this notation. Well, so I'm using in my research work this notation. So sorry, I'm more accustomed to these notations. So anyway, this theta 0, is the original theta. Yeah, this one. And we know such fundamental property for periodicity. Theta 01 is in this notation theta 0, 1/2. So we have this formula. Theta 10 comes from this, and yeah, we can express this in terms of theta like this. So theta 11 is like this. So why should we introduce such functions if we can express everything in terms of theta? Well, yeah, we will see. With these functions, we can have a very compact form of many formulae. So yeah, well, we have still 8 minutes, right? 10 minutes. So let's have a look at several elementary properties first. Since this epsilon 1 and epsilon 2 are, well, actually epsilon 1/2 and epsilon 2/2. So we should consider this K and L as numbers in Z/2Z. I mean, if we have, for example, here 1 + 1, then please consider it as 0. Then we can express these relations between theta functions with characteristics in such compact manner. So if we shift the second parameter, essentially it means that we shift u by 1/2. If we shift the first characteristic, then it is essentially shifting of the variable u by tau/2. So if we shift variable by 1, then, well, it is some case of periodicity coming from this periodicity. If we shift function by tau, then we have another periodicity. But if we shift 1 over 2 or tau over 2, then we have a shift of characteristics. This is the meaning of this formula. And these three theta functions, theta 0, 0, theta 0, 1, and theta 1, 0. Well, in this notation, theta 2, 3, and 4 are even. Well, for example, theta function is even because this is it. And if we sum up all integers, then, yeah, sorry, this is not minus n squared, minus n squared. So if we change n to minus n, then it is just another expression of theta. The other theta 0, 1, theta 1, 0 are even because, for example, theta 0, 1 minus u is equal to theta minus u plus 1 over 2. And because theta is even, this is theta u minus 1 over 2. By periodicity, this is theta u plus 1 over 2 is equal to theta 0, 1. Sorry. The evenness of this can be proved similarly, and the oddness of this can be proved similarly. And well, yeah, so we have our entire function and a case periodic function. So we have no poles, but theta can have 0. And actually, we can prove that in each parallelogram, there is only 1 0 of thetas. And we should prove this. We have only to prove this for theta, the original theta, because as we have seen here, these theta functions with characteristics is just a non-zero factor times theta with shift. So if we prove that theta has 1, 0, then by shifting this parallelogram by some value, we can show that this theta KL has just 1, 0. Yeah, well. And to count the number of zeros, we can use the argument principle. So what does that mean? Number of zeros in this area is an integral 1 over 2 pi I times integral of theta prime u over theta u du. And this is the argument principle, as we have seen some time ago. In complex analysis, this is one of the very useful theorems. And well, this can be written in this form, logarithmic differential of thetas. And this log has such property. Of course, no, this is a property of thetas, just taking logarithm of this periodicity. And by differentiating, we have such form. And well, the integral can be decomposed into 4 parts along each edge. And for example, this we have shift by tau. Here we have also shift by minus tau. So we can write by changing the variable, we have such an expression. So sorry, here we shifted by not tau, but sorry. This shift by 1. And this term, this vanishes because of this. And this is equal to 2 pi I by this. Oh, sorry, by this. Which means that this integral is equal to 2 pi I, and by putting this into this formula, we have this term. So we have proved that theta functions have only 1, 0 in this parallel. Sorry, we have already the time is already up. So yeah, let's continue next week. Okay, any questions? Today nobody asked questions, so I probably spoke too fast.
Okay, thanks.
Sure. So let's meet next week. See you.